now we will review a little bit of calculus to understand clearly what is the gradient. So we will do a lot of function approximation, but over computational graph. So to begin with, we'll just review the definition of the derivative. So I have a function that takes as an argument x, f of x. So here it's the value of f for different x. I will try to compute a linear approximation at a. And to do so, I will use this quantity. So let's say I have a step h, where I go a little bit in front of a. And I will decrease this h to 0. And I will compare the value of f evaluated at x plus h minus f of x. And I will divide by the length of the step. And this is called the derivative of f evaluated at point x here. Or here it will be at a. So it's only an information of the slope. It's an instantaneous slope. So it's like I'm testing here, but then I will go until very close to me, and I have information of the instantaneous, the very local information of this slope close to me. In physics, it's also a speed. If h is the time, it's like having the instantaneous speed. So the linear approximation that I will build is if I want to compute the value of f at point a plus h at this point, I can build this linear approximation by saying that this value is approximately equal to the value of f of a plus the scalar product, again the scalar product, but it's used in a different way. In one dimension, it would only be a product. The product of the derivative here, evaluated at point A, times the length of the step. And so this linear approximation is represented as this line here. And if h is too long, my linear approximation will not be very good for a nonlinear function like this one. So we'll have one error. The error will be this point minus this point. So these two will not be close if h is too far. If I go closer to a by decreasing h, then the two lines match, and this is a good approximation locally. So now we go to n-dimensional space so that I can compute it for my neural network. So f, usually you can think of f now as the loss function. The loss function will take n parameters, like 1 million parameters, and will give me the loss, which will be average over all examples. Now I want to take the derivative of f with respect to one parameter, and so I will note it with this notation. I'm choosing the parameter I, and I'm computing the partial derivative of my loss function. And so my parameter space, let's say I have only 3 dimensions, so I will choose one dimension, and I will test the slope in this dimension. And if I have another dimension, I test on this direction. So this is the EI here. I'm doing it for all the dimension here, for all the n direction. And by doing so, I have one scalar, which is the slope very locally to where I am. And each scalar, one associated to one dimension, I will stack them in a vector. And this is what we will call the gradient. It gives me an information of the slope for all the direction in my space. So we can see that this thing computes in a way, if I move one parameter, how much the loss is changing locally with this linear approximation. And so a differentiable function is a function where this linear approximation here is a good one, where if I take this step h and I decrease it to 0, then the error that I'm doing close to the point A here will be 0. And really, I can write this formula that I can approximate my function by a linear approximation. And this is valid if h is not too far, too big. So here we can see that the error converges to 0. This is what is a differentiable function. So few examples of differentiable function and derivative. So the derivative of a linear function, if x is a scalar, and I multiply x by w, and then I add the bias b, the derivative will with respect to x will only be w. For the sigmoid, it's a little bit more interesting. The derivative of the sigmoid is equal to the sigmoid times 1 minus sigmoid. So the derivative of the sigmoid is expressed as the sigmoid itself. And the ReLU. So the ReLU is a little bit trickier. Remember that the definition of the derivative here, it's the limit of h going to 0. But I can take the limit with h from the left to the right. So I'm taking a h from negative to positive, or a h from positive to negative. And the value of my derivative should be the same, and it will not depend on the direction of the h that I'm taking. So here I have the function that maps any value to 0, any negative value to 0. So the derivative will be 0, 0, 0, and when I arrive at the point 0, the derivative is 0. Here it's the identity function. The derivative of the identity function is 1, and so I have 1, 1, 1, 1, 1, and when I arrive at 0, I have two different values, which means that ReLU is not differentiable at 0. And we don't care in deep learning. Empirically, this problem does not really have an impact on the learning. Even if we land exactly at 0, just choosing one of the two values is okay. It will not change that much. It will not impact that much the learning process. So this is defined in two parts, 1 for this part and 0 for this part. Okay, so another property of derivative that is very useful in deep learning is the composition of function. So I will have one function f that will take x, and then I will give this result to g, and g will be evaluated at f of x. And if I take the derivative of this term, you will obtain the derivative of g evaluated at f of x times the derivative of f evaluated at x. So I'm sure you are having you are remembering when you were in college, when doing this by hand on a lot of different functions. It was painful, and you were asking yourself, why am I doing it when it will be useful in my life? It was for today. Your professor should have told you that it was only for the deep learning course. But really, the composition of function is something that is everywhere in these computational graphs, because when I give my data to a function f, the module will give me the output, and this output will be given to another module. So when I link modules like this, really what is happening is a composition of function. The modules are always reusing the result of the previous function to give the next one.